Hello, everyone. This is the lecture for Physics 112, March 19th. Actually, it's part of the lecture. I'm just going to start off with a review, and then there'll be another part of the lecture which is actually going to be shared with the Physics 102. But what I figured I'd do is I'd review everything since the last test because it's been a while since we actually were together physically in class. And this is a very unusual situation. I thought to avoid any kind of confusion that I would just review everything that we did since the last test. And so today, or sorry, in this particular lecture, it's going to be a short lecture, but I'm just going to review the simple harmonic oscillator because that will be on your next test, okay? There'll be a second part to this lecture, which I'll post the link to in an email as well, but that's going to be shared with both Physics 112 and 102. So that's why this piece is being done separately from the rest of the lecture. Okay, so how this is going to work is all of our material is still up on Free Skies, and what we're going to do is log in there, and we'll go to your course, and then at the very bottom of the course page there are going to be links to PDFs, which would have been the notes that I would have written in class on the projector, only now I've basically just written them and then scanned them, and I'll go over them with the lecture. And then if you have any questions during these lectures, you can always ask them, write them down, and you can ask them during the live chats in the evenings, and there'll be live chats every evening. Okay, so let's go to our website here. So this is www.freeskies.net, and log in using the usual username password, and you should see here all the courses. Oh, let me actually, sorry about this. Let me move my image up here so you can see what I'm going to do here. And I'm going to scroll down here to Physics 112 like that and click there. And you can see, you've got all the usual topics that we've had. But what I did was I added at the very bottom here, you can see where it says online lecture notes. And you can see March 19th and March 19th part 2. So there's actually two links. And in this lecture, we're just going to go over the very first one. So if you click on that link, you should see the PDF. And let me now move my image back down here so that I'm not covering up the PDF. Okay, great. So let's start. So this is just basically a summary of the one-dimensional simple harmonic oscillator that we studied. I'm not going to do any of the problems. We did that in class. This is just sort of like a review or a summary of the material so that you know what's going to be on the second test. Everything we went over in class, but again, given the unusual circumstances, I figured it'd be smart to do it again. Okay, so what is a simple harmonic oscillator? Basically, any object with the mass m, and what it does is it just oscillates symmetrically about some equilibrium point. And so this could be like, for instance, in one of the labs, we had a pendulum which would swing back and forth, or you can attach a mass to a spring like we did on the linear track, and it would just oscillate back and forth like that. The direction of the oscillation doesn't matter; it can oscillate up and down. So you could have a spring on the end of a mass, and then just pull the mass down a bit, and then it'll oscillate up and down like that. And so there's many possibilities. Anything that basically vibrates is going to act to some degree like a simple harmonic oscillator. Okay, and so what you see there in the diagram is me trying to show the best I can the dynamics of that oscillation. Well, actually, the kinematics of that oscillation. So you can see that that dot, and it's going to go along the loop back and forth around x equals 0. X equals 0. That's our equilibrium. That's where the oscillator would just sit at rest if it weren't displaced. Okay. The oscillation is symmetrical about the equilibrium, means that it'll deviate as far to the left as it will to the right. And so you can see there that it will go as far to the right as x is equal to a, and it'll go as far to the left as x is equal to minus a. All right. A is called the amplitude. Okay, we saw that in class. And it just basically is the maximum displacement that the oscillator exhibits from equilibrium. Now, I'm not going to go through all of the mathematics that would prove that that motion is actually a cosine, but you can do that. In fact, I do that for my Physics 102. But let's just start with the fact that oscillations can be modeled very accurately as cosines, okay? And so there you could see that the position as a function of time is going to equal a times the cosine of this omega t. Okay. Oh, A we already discussed, that's the amplitude, and t is the time. Okay, and x is of course the position. But what's this omega? And omega is equal to the angular frequency, and it's equal to 2 pi over capital T, where t is the period. Okay, and this period is the time it would take for one complete cycle to occur. All right, so if the oscillator starts at x equals a, and you just start your stopwatch, tick, 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 it oscillates to one side and then comes back. The time it takes to make that one complete cycle is capital T. So omega is equal to 2 pi over capital T. And you might wonder, why did that 2 pi get in there? And that's just because the cosine has a periodicity of 2 pi. And so what's going on there is when little t is equal to capital T, the capital T's will cancel when you multiply omega t, and you just get cosine of 2 pi, which is the cosine repeating itself. Okay, so that's where that 2 pi is coming in. All right, let's scroll down here. All right, now I did just say that the t is the period. Just be aware that, here, let me just scroll up again for a second. Be aware that omega, this angular frequency, it comes up in the equations quite a bit. So mathematically, omega is a very important thing. But in the lab, when you measure, you don't measure omega directly because you don't have that 2 pi in there. What you wind up measuring in the lab is actually the linear frequency, okay? And the linear frequency is just defined as the reciprocal of the period, okay? And so there's a relationship between linear frequency and an angular frequency, and it's just basically that there's an extra 2 pi in omega, okay? So I just wanted to make sure that was clear, and you're wondering, why do we have these two frequencies? Well, f, the linear frequency, is something that's measured easily in the lab, but omega, which is equal to 2 pi over capital T, that's used in the mathematical equations, okay? And so, well, that's the first point. The next thing is we can ask certain types of kinematic equations about this motion, because all of that information is in the A cosine omega t. And so we might want to ask things like, what is the maximum displacement from equilibrium? What's the maximum velocity that this oscillator will achieve as it oscillates back and forth? And what's the maximum acceleration? And at what points in the cycle do these maxima occur? And so here's the answer. All right. And again, I went through some of the details in class, but I'm just giving you a summary here. So the maximum displacement, that's x max. Well, by definition, that is A. That's exactly what you mean by the amplitude. That's how far, what's the biggest x is going to be, okay? Now, what about the fastest omega? Sorry, the fastest v. Well, the maximum v is actually equal to omega times A, okay? You can see that omega coming up there, okay? So v max is equal to omega A. And what's the maximum acceleration? Well, that turns out to be omega squared times A, okay? And so you can see that there's a very simple pattern there. X max to V max to A max is A, omega A, and then omega squared A, okay? So where do these happen in the cycle? Well, where these happen in the cycle is either at the endpoints or in the middle. Obviously, the maximum x happens at the endpoints because, again, by definition, that is the amplitude, okay? But when you're at the endpoints of the cycle, that's where your velocity is zero, because at that point, the mass has to stop and turn around and come back. And at the moment that it stops, v is equal to 0. And so you could see here, I've got v is equal to 0 on the right-hand side turning point, okay? And so x max is A, v is 0, and also at the endpoints, that's where the acceleration is maximum, okay? So at the endpoints, you have maximum x and you have maximum acceleration, but the velocity is 0. Where does the maximum velocity occur? That occurs right in the middle at equilibrium, okay? At equilibrium, you have x is equal to 0, because after all, by definition, that is equilibrium, where we put x equals 0 at equilibrium. But that's where the maximum velocity occurs. So you've got v max equals omega A at the middle at equilibrium. At that point, the acceleration is 0. It's neither speeding up or slowing down right at that point. It's just cruising through equilibrium at a constant velocity. That's not going to last very long. It's actually just locally around x equals 0 do you have a velocity omega A. As you start to approach the endpoints, the velocity is going to decrease until it finally stops at the endpoints. Okay, and so I just have that summarized here. Okay, again, X max and A max occur at the endpoints where V is equal to 0. V max occurs at equilibrium where X and A are equal to 0. Okay, now that covers the kinematics of the simple harmonic oscillator. That is position, velocity, acceleration, and how they relate to one another. Uh, the next question is one of dynamics. Okay, like what causes something to undergo simple harmonic motion? How would you have simple harmonic motion occurring? And the answer is you have to have a restoring force, which is proportional to the displacement x. In other words, that's Hooke's law. Okay, so what Hooke's law says is, if you have an object, which like a mass attached to a spring, but it could be any object which has some stiffness associated with it, and it just sits there at equilibrium. If you grab this object and you pull it away from equilibrium, there's going to be a force that wants to restore it to equilibrium. Okay, and the further you pull it from equilibrium, the bigger that force gets. Okay, so the force is actually proportional to how far you pulled it from equilibrium. And so there you go. This is, you can see at the top of the screen there, F is equal to minus kx. That's Hooke's law. Okay, F is the restoring force. It's the force. You can see it in the diagram. That's F trying to pull the mass m back to the origin, back to x equals 0, the equilibrium point. The other thing is that F and x are in opposite direction, and that's why you see F is equal to minus kx. The last ingredient in that equation is K, which is the spring constant, and it's a measure of how stiff the spring is. In other words, how hard is it to stretch that spring? Okay, and so, uh, like I say, it's this basic. Oh, I went a bit too far. Let me scroll back up. Okay. Basically, a classic example here is a spring attached to a mass. All right, with a restoring force. All right. Now, I can't do all of the mathematics behind this, but it turns out that that angular frequency, which was equal to 2 pi over capital T by definition, you can show that in the dynamics of a mass m attached to a spring with constant k, you can show that the angular frequency is given by the square root of k over m. Okay, and so that kind of makes sense from a physical point of view. The stiffer the spring is going to be, the faster the object will vibrate. So you can imagine a very loose spring, a spring with a very small k. If k is very small, omega is very small, and the oscillation will be very slow. So you pull this out, and with a slow, try it this way, you pull this out, and then with a small k, it'll oscillate back and forth slowly. But as you increase k, if it's stiff and you pull this out, it's going to be pulled back faster and it'll oscillate faster. Okay, and so omega is well, it's not proportional, but omega will increase with k. Conversely, omega will decrease with m. Okay, so you might have the oscillator here and you pull it out, but if it's a very heavy mass, the force doesn't have as much oomph in terms of accelerating it, and so again, it won't oscillate back and forth quite as fast. So the bigger m is, the lower the frequency of the oscillation is. Okay, now the next point that we're going to study is the energy of the oscillator. And since there's no friction in a simple harmonic oscillator, I know in the lab we looked at a damped harmonic oscillator, but for a simple harmonic oscillator, there's no friction. And if there's no friction, there's no loss of energy over time, and so the energy is conserved. And basically, you could say, okay, I can calculate the energy by just adding the kinetic energy plus the potential energy of the oscillator at any point in the cycle. So if at any point in the cycle you can calculate the kinetic energy, you have enough information to calculate the kinetic energy, and you have enough information to calculate the potential energy, you add those two energies together and you get a total energy, and that total energy is constant. Okay, even though you calculate it at one point in the cycle, it'll be the same value at every point in the cycle. Okay, and so at the bottom there, you can see that I have E is equal to the kinetic energy plus the potential energy. But now we can say, well, what's the kinetic energy given by and what's the potential energy given by for an oscillator? Well, the kinetic energy is the same for all objects that are moving. It's 1/2 mv squared. That's no different whether it's an oscillator or just, I don't know, a car going down the street or whatever. It's 1/2 mv squared. But the potential energy for an oscillator is the potential energy due to the spring being stretched. Okay. Now, again, I gave you this last This came up last semester when we were doing energies, okay? And I didn't prove it there, and I'm not going to be able to prove it now because this actually takes some calculus to do that. But we could just take it as given that, if you have a spring with spring constant K, and you stretch it a distance x, then basically that spring has potential energy 1/2 kx squared. So you can notice that as x increases, the potential energy increases, but it actually increases as x squared, not linearly. Okay, so uh, we get three possible ways of expressing the energy. Okay, two of them are for special points in the cycle. So if you're at one of the endpoints of the cycle, okay, x is equal to a, or x is equal to minus a, it doesn't matter because once you square x, you get the negative sign goes away. So if you're at one of the endpoints, there's no kinetic energy at the endpoints because v is equal to 0, and x is equal to a, and so that equation that adds the kinetic energy and the potential energy just reduces to 1/2 ka squared. Again, the kinetic energy is 0. Why? Because 1/2 mv squared, v is 0, so the kinetic energy is 0. So all the energy is potential at the endpoints. Okay, all the energy is in the potential energy, and the potential energy at the endpoint is 1/2 ka squared because x is equal to a at one of the endpoints. All right, and whatever that energy is, it's the same energy everywhere. Okay, so it just might be the case that in a problem I give you what A is and I give you what K is, boom, you have the energy. Okay, conversely, you might not know what A is, but you know what the maximum velocity is. That is, you know the velocity as this thing passes through equilibrium. So when the thing is passing through equilibrium, it has a maximum velocity, and so it has a kinetic energy. And the kinetic energy, you can see it written there, is 1/2 mv max squared. We're looking at the second box now, the equation with the second box around it. And all the energy is kinetic. What about the potential? Well, at equilibrium, x is equal to 0. The spring is not stretched at all at that point, and so it has no potential energy. And so all the energy is kinetic as the mass passes through equilibrium, and therefore the energy is 1/2 m v max squared. Again, you may have v max, I may give you v max, I may give you m. Now you have the energy. You can calculate it at equilibrium, but it's the same energy anywhere in the cycle, anywhere in the cycle. Okay, so there's two possibilities. And the third is, well, what happens if I give you enough information, but it's at some other point? It's not it's information, but not at the end point or at the middle. Okay, and so then you can use the general equation, which is basically that the total energy is equal to 1/2 mv squared plus 1/2 kx squared. And you'd want to use this equation when you want to calculate the energy at any arbitrary point in the cycle. Okay, so I'd have to give you all of the things there. I'd have to give you mass and k, and then I would have to tell you what the velocity is and at what position, what value, what displacement x that velocity is obtained, and then you can put that all in there and you can calculate the energy. Conversely, you can use any three of these, any one of these three, to get the total energy, and then use it in any of the other ones. Because once again, if you can calculate the energy at any point in the cycle, it's the same energy at every point in the cycle. Okay, because energy is conserved. All right, and that ends the lecture. Let me just show you what problems you should be doing for this. If you go back to our course here, okay, and you scroll to actually, well, I lost the capture. This happens sometimes. I can't seem to get the capture back. There we go. Okay, so let me just move my uh, let me move my image up here. Sorry about that, guys. I'm still getting used to this OBS Studio. If you just scroll up here to the section that says simple harmonic oscillators, and then you can see here there's some sample questions, sorry, assignment questions there. There's what do I have there? 3 questions on simple harmonic oscillators, and maybe we could just take a look at the first one, but I don't want to do them for you. The solutions are online, but work on them because they're the kinds of things that are going to be on the test. Okay, so in the first question, I give you the mass is a 1 kilogram oscillator is attached to a spring with spring constant 5 newtons per meter. As it oscillates, it is observed that the mass passes through equilibrium with a velocity of 10 meters per second. Okay, and then I ask you a series of questions. And let me just point out, I'm not trying to be tricky here, but notice that I indirectly give you what Vmax is. I say the velocity as the mass passes through equilibrium, and you're expected to know that when the oscillator passes through equilibrium, that's when the maximum velocity is obtained. So actually, I've given you three things there. I've given you that the mass is 1 kilogram, that K is 5 newtons per meter, and that Vmax is 10 meters per second, and then you're able to answer all the other questions. Okay, so I'm going to end the lecture here. If you have any questions, of course, you can always ask them during the live stream. And well, there it is.